All right. So it's a little lighter crowd here today, probably because of the rain. What's ES3? You've got a test in ES3, right? Oh, they just had one. Anybody in ES3? How'd the test go? You guys know all you need to know about Thevenin equivalence and Norton equivalence? We do, but what?
I mean, I thought I did.
The what?
MATLAB.
MATLAB. You had a test on MATLAB?
Yeah. So we had previously done just solving matrices in MATLAB, and then he gave us like this string concatenation thing.
What's that have to do with Thevenin equivalence? Huh. That's a good question. Anyway. All right. Well, I hope you did all right, and I hope everybody else is recovering, and I hope you're watching this on YouTube. OK. So here's what we're going to do today. We started. Hello. We started trees yesterday or on Monday, and then today we're going to talk explicitly about binary trees, and then we're going to go through different functions you can do with binary trees, and then you guys are going to actually solve a couple binary tree kind of recursive programs. Somebody, I forget who it was, asked about recursive programs the other day. We're going to practice some more recursive programs with binary trees. They happen to be very well suited to nice, beautiful recursion type ideas. OK, so we'll look at a little bit of that. All right, any questions before we get going? Homework 3 on anything else? We have started grading homework 2. It should be by next week, by the beginning of next week. I definitely want to get it to you before this next program's due, and hopefully before the mid-year next week. No questions? All right. Here's what we're actually going to do today. Unix tip of the day. I've actually got I think it's a fun Unix tip of the day. I think you'll enjoy that. And then we're going to talk about binary trees. Last time we talked about postfix notation. Today we're going to talk about infix notation. We're going to review postfix a little bit, and then we're going to do a little bit of prefix traversal, and you'll see how different traversal strategies. And then I forgot one traversal strategy called level order traversal, which is an interesting one. It's actually very you can see it like when you're looking at a tree. You can say, oh, I can easily pick out level order, but it's much not harder, but it's trickier to actually code it up. So we'll talk about that. Then we'll talk about binary search trees. Remember how I had I showed you the array that was sorted, and I had it kind of drop down into that nice tree that I put it on the board, and it dropped down into that nice tree form? Well, binary search trees, that was a binary search tree, and they're very good for doing searching and whether or not a tree has a node, has a particular value, and so forth. So it's nice. We won't get to sets again today, unfortunately. But we'll talk about how to do a bunch of functions with the binary trees as well. OK, and we'll talk about the asymptotic analysis about that too. All right, Unix tip of the day. So if you go onto the homework server, many Linux systems have this program I'm about to show you, but sometimes they don't, and ours doesn't. So I actually installed it for you on comp15 public_html cowsay, and then you have to type cowsay again. And if you type cowsay and you say something like, hello, I'm a cow, right? Then watch what it does. Well, it doesn't do anything, so I didn't put the final. Let's see. Oh, sorry, I'm doing the wrong one. Here, there we go. Hello, I'm a cow with. Let's make it double quotes here instead of single quotes. Oop, wrong one. There we go. All right, hello, I'm a cow, and then it does that. Right? And it's a little ASCII art cow, right? And you can actually make the cow. I know, isn't that great? ASCII art cow. Let's see if I can go back here. I should change the color of the cursor here because I can't even see it. If you do cow think, watch what happens. It's a little like think bubble, right? Right, a little think bubble. What's cool about this is actually kind of neat. I mean, he'll do anything, right? I mean, you can say, 420 fields ago, right? Whatever, right? And he'll read the whole thing off to you, and it's kind of fun. But what you can actually, what's kind of neat about this version is that if you type cow think and then -L, it actually gives you a list of a whole bunch of different ASCII art things, right? So which one should I do? Hold on. I'll try satanic, then I'll do stegosaurus. I don't know if I've done satanic, so hopefully it's not bad. But satanic, let's see. You think you're going to heaven, huh? Right? Oh. Right? Yeah. All right, what did the other one? You want to do stegosaurus? Well, we'll try a couple. Don't worry. Hang on. How do you spell stegosaurus? O-S-A-U-R-U-S. Let's see. Too bad I'm extinct. Too bad I'm extinct. But do you like my hat? Right? Okay, what was the other one you wanted to do? Dragon. Hang on. All right, hold on. You guys can try all these on your own. No, I don't like dragon as much. Well, koala. What? Hold on, I'm going to do koala first. This is a koala. K-O-A-L-A. That's not bad. Not too bad. What did you say, Vader koala? Oops, hang on. Like that? I don't get it. Well, anyway, so you can check that out. Okay, so that's online. You can check out you can check that out. Now, if you happen to be on a question? You can edit the files and make your own, sure. Yeah, you can go into that. Well, you can't on. I haven't given you permission to do it on this one, but if you want to download it and run your own, you can make your own. Sure, make your own. Whatever you want. You can make a Yoda koala or something. I don't know. So if you happen to be on a Mac, okay, there's another command called say, right? And you can say something like this. Would you like to play a game? And if you know that reference, you're. Oh, let me. Right? So the best part about this, and I will not confirm nor deny whether I've done this before, but let's say that your girlfriend has a Mac and she's across the room and you know her SSH password, and you can SSH, and all of a sudden her computer says something like, "Would you like to play a game?" Right? Or so I mean, whatever you want, right? Hey, baby, you type pretty well, whatever, right? And she goes, "Oh my God, my computer's talking to me," and then you laugh, and then she dumps you. But anyway, so that's that. So you can do that as well if you'd like. Questions on cow say or cow think? Go ahead and play around with it. It's kind of fun. Okay. -L. Cow say -L. All right, and now you should pay attention instead of playing cow say. Okay. All right. Okay, let's go into trees again, binary trees. Remember, I've created a monster. Okay, remember, binary trees are simply, they have a left and a right, and we talked about these expression trees, and this was A times B. Okay, an expression tree A times B. All right, that was from last time. Okay, if we want to do what we call an in-order traversal, okay, in order traversal says do this as if it was a regular infix notation like you would do in math class, right? Like you've known since you were like in 2nd grade, right? And so what this stands for is in order traversal would be A times B. Okay? And the question is, how are we going to program A times B? And remember how if we don't know the order of operations, we have to parenthesize it? So what we're going to try to do is actually parenthesize this and print this out. So I just want to walk through the idea for that. Who remembers the algorithm for postfix? If you're doing if you are doing a traversal, right? TRAV, well, let's say it's postfix traversal, right? What did we just say we were going to do for the postfix? There was a really simple algorithm. Yeah?
When you hit a number, you push it.
Ah, OK, that was for the stack-based thing, right? That was very good for stack. But in terms of just going through the tree, we have a nice, easy, recursive algorithm about how to go about doing the postfix. Alan, do you remember?
Go left.
Yeah, there you go, right? We basically traverse left. This should be like node, right? Traverse node left, right? Then what do you do?
Then traverse right.
Traverse node right. Traverse node right. OK. And then what do you do? Well, don't we need to do any traversing. Let's say we're trying to print this out. What do you do after you've traversed left and traversed right? Print yourself, right? Just print the node. In this case, maybe node data or something like that. And that's the whole postfix algorithm. It's really simple. It's very beautiful in the sense that it's just go left, go right, print. And what that does for postfix, it says go left can't, go right can't print. So it prints A. Back up here, go right, go left, go right, can't, print B, return, print yourself, so it goes A, B, star, and that was postfix, right? OK. I want to know how we would do this exact same thing for infix, which means it's going to be A times B. Alice? Sure. Print node data is going to go right in between here. I should have left more room. Print node data. Right? Now it's going to go left. When it returns from going left, it's going to print itself. And then when it returns, and then when it stops printing itself, it goes right, and it does this as well. Right? Go left, can't go left, print, can't go right. So A, back up, print star, go right, can't go left, print, can't go right, return, we're done. Make sense? OK. How do we parenthesize this now? In other words, we want to make it go, we want to overly parenthesize it. We want to parenthesize the whole statement, right? We want to parenthesize the A, and we want to parenthesize the B, and we want to parenthesize the whole situation. Where might we add to our little program here? Susanna? The beginning and the end. I like that. What are we going to put at the beginning? Yeah, so I'm still running out of space here. So what would I print right at the beginning here? Print, and you said open, I don't know. Let's not do it with a little, let's just say print open, sorry, that's a closed, there we go. Open parentheses, something like that? Yeah, OK. And then what else would we have to put in there?
At the end, we'll put
Down here? What are we going to put there?
like a closing.
Close parenthesis. Would that do it? Let's walk through it and see. OK, starting at the star, because that's the root, print an open parenthesis. OK? Traverse left to A. Traverse left again at A. Can't. Print A. Did we miss something? Oh, we did. I totally missed a line. Traverse left to A. Print open parenthesis. Right? Then traverse left, you can't. So print the data, A. OK. Traverse right, you can't. Print a close parenthesis. And then we're going to return. And we just traverse left. So we're going to print the data, star. Right? And then we're going to traverse right, which means go to B. So traversing right, we have to print another parenthesis. And at B, it's the same thing as it was at A. And I won't walk through the whole thing, but it's going to end up like that. And you're going to return twice and print 2 parentheses. So far, so good? OK, let's see if that's what we came up with here. I called this one in order, binary node. We forgot. We forgot our base case. Right? Our base case is if node is null, return. We always got to remember that. So I totally forgot that. Print left parentheses, left child, print the symbol, right child, print the right parentheses. OK, good. This is overdoing it a little bit. Right? Don't you think like this is like too many parentheses in this case? OK, if you happen to know some order of operations, you don't need all those parentheses. OK, how might we do it to get rid of the parentheses around just the A and just the B? Think about that for a second. Yeah. There we go. Isn't that the only? Is that what you're going to say? So the only time you're not going to print parentheses is if this one's not null and this, or if this one's null and if the left and the right are null, because then it's just a symbol and there's no other. You know that it's not an operand, right? OK. I suppose in our case you probably could say if it's not an operand if you knew what an operand was, right? Or yeah, if it's not an operator, you could probably do the same thing. But yeah, so we would just have a little if statement in here. If left and right, or if not left and not right. Does that make sense? If not left and not right. Yeah, I mean, you basically check and make sure that there's no left or right for the node. And then you would not print it. OK, so I like that. There we go. If the node has a left child, print the left parenthesis. Sorry, I did it kind of. Yeah, you only need to check which one when you're doing left. The open parentheses. The left node, right? You don't need to worry about the left child. You don't need to worry about the right child for the open parentheses. Because, well, I guess you technically could, but in this case, there's not going to be a node with only one child. So that's probably the big reason there. But does this make sense? Doing it this way, you would now just print out the parenthesis A times B parenthesis. OK? And you might run into problems with order of operations for this one. Right? Because in this case, you're just printing it out, and it might not be the right order of operations that you thought, like with this form. OK? But that's the in order traversal. OK? All right. Start us off with what this represents. What's the in order traversal for this one going to be? What's going to be the first thing that we're going to print? Let's see. You're going to go left. Well, you're going to do a parenthesis right first, right? Parenthesis, parenthesis A, right? And then what?
Plus B times C.
Plus, are we going to have another parenthesis? B times C, and then all of that in a parenthesis. Yeah, there's going to be lots of parentheses here, actually, right? Yeah, tons of them, right? If you've got the over-parenthesized version. But that's the order they're going to go in, OK? You can kind of see like it's going from left to right, but going, wrapping around and kind of like that sort of traversal. OK? In this case, kind of the halfway point that gets printed is the plus. And that makes sense, because that's saying add the whole left plus the whole right, and it's going to be right in the middle. OK? But that's how it would look like. If you didn't overly parenthesize it, it would look like that. OK? And actually, you know what? I think order of operations would actually work on this one. Like as long as it's, I think order of operations would work on this now that I think about it. But, yeah. Anyway, that's what the in-order traversal looks like. We already did post-order traversal. This is what we just talked about. OK? One thing I want to show you, there's a little animation online that you can go to. And let me see if I still have it up here. Yes, I do. You can go to the, might already be started. Let's see. One of those cases where, there it is. OK. Let me move this. Let me make this a little bit bigger so we can see it. All right. So what this is going to do is this is a binary tree, right? It's not a binary. It's not in any particular order. It's just a binary tree. But what you can do is you can say do all the different types of ordering, right? So if we want to do in order, I'm going to make this go a little faster than it normally does because it's super slow. In order, watch what it does. It goes and prints that one. Then it comes back up and prints that one. Then notice it's doing this in order traversal that we talked about. Okay. All right, and it goes through and does the whole tree in order. And if you get confused about what the orders are, go to this website and then try it out. Okay, and you can see the orders. All right, post order. What's the last thing that's going to get printed in post order in this case? What's the last thing that's going to get printed? Right? Remember, it's go left, go right, then print yourself. And 98's the root, and it's going to go left, go right, and then eventually get back up all the way to 98 and print itself. Right? Ta-da. Okay, I won't show you the pre-order, although pre-order kind of does it. It prints the 98 first, and then all the rest of the tree. Okay, there's also one called level order, which we'll talk about in a couple minutes. Okay. All right, questions on that one? Go look at the video. Yeah, David.
So
or go look at the.
if we were to actually be implementing the example you gave of the appropriate number of parentheses
Yes.
in order,
Yeah.
have it return like a Boolean indicating whether or not it was null or not. Is that the easiest way to do it? And then check each time and like save that in two variables and then do a check because you couldn't actually call the function again. That would mess everything up.
What do you mean? What do you mean? Why would we need to call the function? Why would we need to check?
Well, because we need to determine whether or not both the
Oh,
traversals
sure.
were null or not.
Yeah, good question. You've got a node, right? If you've got a node, you can say if node left, right, equals null, etc. You can do that. You don't have to call the function again. You can just refer straight to it.
Okay, so we're just gonna, I guess, isolate the development of it will return null. We can guarantee that the other function in the same function actually.
Right.
And then later just check to see if it's null.
Just check. Well, yeah. If you're going to have to check and see if before you print whether or not the child is null, then you can just straight up check it.
Yeah. Okay.
Yep. Yeah. Good question. Good question. All right. So that's post order traversal, right? This is what the order of the numbers would be, right? It's going left and then all the way right because it can't go left anymore, and then back up and so on. The last one that gets printed is the 13. Okay. And that's how it ends up coming out. And this is postfix notation, like we saw before. Okay, postfix notation. Kind of cool. From the expression tree, we can get the postfix notation out of it. Okay, no stacks necessary. We're doing all this with trees. Okay, all this with trees. Okay. There's pre-order, which I mentioned, but I won't show you the animation because eyes start to bleed after a while. But you can look at this one. The first thing that gets printed is the root, and then the last thing that gets printed is the thing all the way over on the right. Okay. Go ahead and you can check all this out. For what's the pre-order recursive algorithm? Yeah. Print, go left, go right. Right? I mean, there's only a couple different options in that case. Okay. So that's postfix, infix, prefix, right? There's also level order. This one takes a little bit of thinking. All right. With postfix, prefix, and infix, we used the recursive algorithm, right? And it's a very beautiful recursive algorithm. What did we say that recursion is really using under the covers? A stack, right? So you can implement postfix, prefix, infix all with a stack. Level order, you can't. Okay? You can't figure out, at least I don't believe it's possible with one stack anyway. You might be able to do it with a couple different stacks or something. But one stack, you can't do level order. Because watch what happens here. First, you do this. What level order? Can somebody figure out what level order really means in this case?
Printing everyone that's on the equivalent, like one step down.
Printing everybody on the same level in the order from left to right. So first you print this level, level 0. Then you print level 1. Then you print level 2. And then 3 and then 4, right? Notice if you try to do some sort of recursion on this, you go down this path, but then all of a sudden you have to like blast over to this path, and your recursion is dead in the water, right? It's really hard to come up with a, I don't even know if it's possible to come up with a recursive algorithm to do the level order. Okay? Well, any ideas how we might do it? This is actually a little tricky. What's that? Did I say? Oh. Anybody want to read the slide? Right? What are you going to use in this case? You're going to use a queue, as it turns out, which is kind of neat, right? Watch this. OK. We have a queue. Remember, you insert and then remove from the, you insert at the back and remove from the front. OK? Watch what you can do in this case. If we insert the plus, OK, we insert the plus and then immediately dequeue the plus. Once we dequeue the plus, the front and the back will be here, right? Because we dequeue the plus, OK? And then we take that plus and we inqueue its left and then inqueue its right. OK? So read off what the left and the right of the plus are. The first plus. Plus again, and then star. OK. Now we dequeue the next thing, which is the plus. And by the way, so I dequeue the plus and then print it. Now I'm going to dequeue the next thing, which is also a plus, and I'm going to print it. But then I'm going to inqueue this one's left and right, which are which ones? A and star. A and star. OK? Then I'm now on this one, because this is now the front of the queue, right? I'm not going to move it, but this is now the front of the queue. And I dequeue it and I print it. And then I inqueue plus and G. See how I'm doing it in level order now? And I'm dequeuing in level order, like the first in, first out. That's exactly what has to happen in this case. Yeah, so center. It would, sorry. Back is going to be over here. Yep, and front is going to be wherever I last one I dequeued. Front, back, flip back. Yeah. Yep. But that's exactly how you have to think of this. OK? You guys will do this in the lab on, I believe, next week. You'll do a Q lab. Yeah?
So we can't do it using recursion?
I don't think there's a way to do this with recursion.
Can we just call print the first node's next and the first node's left data, and then print the node's right data, and then recurse?
Well, recurse how? Because now you've got to think about what you've got to do. You've got to recurse to this piece at the same time as you're recursing to this piece. And then you've got to recurse to like this piece and what was it? This piece. And then also, see what I mean? So I don't think it's possible in that case. If you can figure it out, awesome. Yeah, but I've never figured it out. Yeah, Josh.
Some kind of a level counter. So you could say go until you're on level 1, and then you go to the other one until level 1, then increase that by 1. Go to the left until level 2, to the right. You could probably do that. That sounds more like an iterative solution than a recursive solution, right? I mean, if you're trying to do it, I don't know that it's possible to do it recursively. You can certainly do it in iteratively. I mean, that's really what you're doing with a queue anyway. You're doing some sort of iterative process, but it's sure, you could write it that way if you wanted to, I'm guessing. Yeah. But you see how this actually works, though, right? And that's called level order. And a lot of times you want to print level order. What's really tricky, if you want a tough problem, figure out how to print a binary tree on the screen such that it fits. This is a hard problem, as it turns out, right? Think about why. Let's say that you're trying to print this, but let's say C had a right and had a right and had a right and had a right and had a right, and you had one way down here, right? How do you figure out where all the correct spaces and tabs are to make, because this would have to be a lot wider, right? It's tricky to do. I've tried it a bunch of times, and it keeps my, I keep scratching my head about exactly how the best way to do it, right? But it's possible, and there's certainly algorithms that do it, but it's hard to come up with. So that's a good programming challenge. If you want something like challenging out of this, input a binary tree and then try to print it to the screen, which would be by definition level order, because you want to print the first line, then the second line, and the third line, and make it so all the tabs work out. Right? It's tricky. Yeah, I see Josh going, oh, what are you talking about? Yeah, it's tricky. Okay? Be a good programming challenge, though. If you need something a little more challenging, that's it. OK, questions on level order. OK? Let's move into binary search trees. OK, so we already mentioned binary search trees the other day when I did that dropping down of the array that was sorted, right? And you noticed that it came out to be a nice tree that had a cool property, right? And that property was what? If I have a node here and I'm doing a binary search tree, what's the property of everything on the left? Less than the root. And everything on the right? Greater than. OK. In computer science, we call that an invariant. OK, what an invariant means is that this is the rule for the data structure or the abstract data type. The rule is, in this case, if you have a proper binary search tree, everything on the left is less than whatever node you're at. Everything on the right is greater than whatever node you're at. And if you screw up and put one in the wrong place, you don't have a binary search tree anymore. You might have a binary tree, but you won't have a binary search tree anymore. OK, it's called an invariant. And we'll talk about that for a number of different types of data structures and abstract data types later, right? The invariant is, in this case, make it smaller on the left, greater on the right. OK, that's the invariant. OK, and this is the technical definition here. Okay. All right. The tree on the left is a binary search tree. The tree on the right is not a binary search tree. Why? Seven. Yes, I heard it a bunch of times, right? 7 is incorrectly placed. Why? Because it's greater than 6, but it is in the left part of the tree of 6. So this is not a binary search tree anymore. David?
Yeah, it's a quick question. On the last slide, it said that everything on the left side would be less than.
Yep.
Would it be less than or equal to?
OK, equal to is a tricky one. In most cases, we are going to not have duplicates in a tree. You can have duplicates in a tree. You kind of just decide whether to put it left or right based on whatever you want, really. But in general, what we do is we hold a node and we say if there's, let's say there's 2 7s, we're just going to say that that node has an extra little thing that says, hey, there's 2 of us. That's how you would do it, right? You would keep one node and just have a counter of how many times that node is. That's generally what you do. Yeah, generally what you do. Good. OK, binary search tree, not a binary search tree. The cool thing about binary search trees is on average, and this is again on average, so if you took random numbers and started putting them in a binary search tree, keeping the invariant true, you would end up getting, on average, logarithmic, or the log base 2 of the number of nodes depth. OK? Because basically, you're saying, on average, we're splitting the tree in half. Half's going one side, half's going to the other side. And each node splitting in half, half to the left, half to the right, all the way down, right? That's an average thing. So when we talk about things like asymptotic behavior, yes, we could have a degenerate tree, OK? A degenerate binary search tree that still is a binary search tree, but it's also but it's actually like not this logarithmic behavior, right? If I had, well, give me an example of inserting into a binary search tree where that might not happen. Might not be like nice and what we call balanced on the left and the right. What kinds of numbers would we have to insert? I'll start you off. 1. Yeah. 2 goes here. 3 is bigger than 2 goes here. 4 is bigger, see what I mean? Right? If we added a 0, that would be nice because then we'd get a 0 here, right? So you can, but if you can get a degenerate case. But if you did like random binary search trees with random numbers, it would on average be logarithmic in height, which is great. Because if we're trying to search through the tree to find things, how many maximum levels down do you have to go? A log of the number of nodes, right? And remember, log n behavior asymptotically is very good. OK, it's not the best. It's not constant, but it's very good. If you can get logarithmic behavior on average, you're doing things right. OK, you'll be very fast in your overall algorithm. OK, and logarithms grow slowly, so that's great. Okay, what's the logarithm base 2 of 1,024? Any ideas? 10. So if you have 1,024 elements, the maximum number of search down you have to go is 10 items. That's pretty cool, right? If you have 2,048, you only have to go 11, right? Because that's the way logarithms grow, right? Twice as much, all of a sudden only, only one more in terms of the logarithm. So very nice. Okay. All right. We have to come up with a couple methods or functions for binary search trees. Okay. I'm breaking this into two categories, easy, and there's one hard one. Okay. Let's go through the easy ones, because I know most of you guys could knock them right out of the park if we tried to do it. Think about this. How would you find the minimum of a binary search tree? What algorithm might you use? I'll let a couple other people. Let's think about it, and then I want to see a few hands to find the minimum. Okay, a couple people. What were you going to say?
I was just going to say you go as far to the left as possible.
Is that what everybody was going to say? Go left, go left, go left until you hit null, and that's the one where you were about to hit null is the minimum. Isn't the farthest left node in a binary search tree always the lowest node? It has to be. Because otherwise, if there was anything to the left of it, it would be less than it by definition. So that's easy. OK, what's the asymptotic behavior of finding the minimum? On average. Logarithmic, right? Because you might, in fact, you might have to go all the way down the tree, right? And you might have to go all the way down the tree for the logarithmic, on average, logarithmic behavior. OK, what is the best case scenario asymptotic behavior for find min? Constant, because what? It could be the root could be the minimum. Everything is to the right of it. OK, what's the worst case? Linear. Why? It's degenerate. All of them are, right? It's just goes 6, 5, 4, 3, 2, 1, and that's all the whole tree, and you have to go through all of them. So those are the best case, the best, worst, and average. The good news is most of the time you'll hit that average pretty close, OK, for a binary search tree. All right, that was a pretty easy one. Find max. It's exactly the same thing except go all the way right. OK, that's your maximum. Great. Same behavior too, by the way. OK, how about contains? In other words, contains 4. How would I do contains 4? And you return true if it contains 4. False otherwise. How would I do that? Think about that for a sec. You can actually talk to your neighbor if you want and say, this is what I think. OK, what do you guys think? Somebody from the back who hasn't answered in a while. Yeah. OK. OK, so you go to the node and you check it and you say, if what we're looking for is less than the node, go left. Then go to the next node. If it's less, go left. If it's greater, go right. Right? So that's how we would find 4. 4 is less than 6, go left. 4 is greater than 2, go right. You found it. Pretty simple. And what happens, and how do you know you haven't found it? If all of a sudden you get to a null and you haven't found the number. Good. That's a pretty easy one. OK. So those three are. How about insert? How's that one going to be?
Does it have to be in the right place?
It has to be. Does that have to be in the right place? Yes, it has to be in the right place. In fact, is there more than one right place for a node given a current binary tree? Alice?
I don't think so, but I was going to ask, would you insert it again if it's already there?
Yeah, this is back to what Dave was saying. If you, in general, you don't insert it again. What we generally do is we just keep a counter and say, oh, we're inserting 4 again. Now there's 2 4s. And we just keep a little counter in the node. We make the node have one more variable that says counter. That's generally what we would do. Sometimes you could add another one, and you just pick left or right, maybe even randomly about which one you want to go with that one. But good question. OK, so what's the insert algorithm then? Like, how are we going to insert 5? Talk to your neighbor. Okay, somebody from this side of the room. What do you guys think? How do we actually insert into the binary tree? Yeah, go ahead, Isabel. You do the same thing as contains, and then when do you know that that's the place you insert? Null. I know, and it's null, right? If I want to insert 5, okay, 5 is less than 6, go left, like contains. Okay, 5 is greater than 2, go right. 5 is greater than 4. Hey, look, the right hand of 4 is null. That's where we put it. And Alice, is this the only place we can put 5? Yes. There's no other place on this whole tree where we could put 5 without moving other nodes. Okay, so there is a definite place. Okay, so those 4 are pretty easy. Okay, so far so good. Those 4 are pretty easy. Let's see if we got them right. Find min, start at the root, go left. Yup. Find max, start at the root, go right. Okay. Does a tree contain x? Basically we got it right, right? I mean, if the tree is empty, you're going to return false because it doesn't exist, right? If it's null. If it's the node, return true, and then call either left or right depending on the relationship, greater than or less than. How would I do greater than or less than if I was storing, let's say, people's names? Alphabetically, right? So we can store strings. If we have a class, we have to determine what we're comparing, right? Let's say we had a student class and we were comparing, we had a last name and a first name. Well, you're going to want to compare one or the other, or maybe both in some form or another. But you can still determine greater than or less than or equal to. Right? You can still determine that in general for whatever class. And you have to be able to do that for this to work. Okay? Question, Joe.
So I understand based on the algorithm for inserting something and also just by logic when you're looking for it that say if you got something like 0, you'd want it to be in the far left to the left of 1.
Sure.
But would it make it not a binary search tree if it was to the left of 3?
You tell me. If 0 was here, why does that break the binary search tree? Because 0 is less than 2, and it's got to be greater than 2 to be on the right side.
So that travels all the way up.
Absolutely, yeah. It's whatever node you're at, everything to the right of it has to be greater. Everything to the left has to be less. Okay, good. Yeah?
So let's say the 6 was a 7.
Okay, let's say the 6 was a 7.
And the 4 was a 6.
Oh boy, let me write this. Let me just draw this down. Okay. Okay, so you're saying we've got a 7 and a 2 and a 6 and a 1 and a 3 and an 8. Okay, now what's your question?
If you want to insert 5 now, would you have to rearrange everything the way that
You tell me. 7 is what to, so which way do I go for 5? Which way do I go? Which way do I go? Which way do I go? Still works. Woohoo! Right? It actually works because it, it's just you're just going to travel farther. That's all. Yeah, good question. Very good question. Okay. Now, we've done what I call the easy cases, right? We've done insert. Insert was right. This is the special case I was talking about. If they're the same, we might want to keep a list of duplicates. Okay, if you want to do that. Recursively call left or right depending on x's relationship, and then if you get to null, stick it there. Okay? All right, we talked about how to insert 5. Okay, remove. Okay. So this is where things get a little bit hairy. Okay? Here's what I want you to do. Talk amongst your neighbors and figure out 2 things. Thing number 1 I want you to figure out is there are 3 cases for remove. Okay, in other words, if a node exists, it could fall into one of 3 different cases. Figure out those cases. Step number 2, try to figure out for each case what you have to do. Okay, take about 5 minutes, 6 minutes to do this, okay? Talk to your neighbors, figure out how we might remove this. There are multiple answers. There's one that I think is particularly clever that we will talk about, but hopefully maybe somebody will figure it out. Somebody did in the earlier class. Okay, give it a shot. Yeah. If you were to remove 2, you would want to, you'd have to do something to keep the tree a binary search tree. Yes. Something like that, yeah. You'd have to figure out there's a way to do it that's a clever way. There's a number of different solutions, but that's one of that. You have to figure out how to do that for every case. That's the. Yep. Well, okay, but 2, okay, 2 is a good example. 2 has a left and a right. If we just stuck, well, what were you trying to do in this case?
You're on the left side of the tree and you delete something.
Which one?
You go to the right node and try to
Okay, take one.
You're on the right side.
Oh yeah, but that you have to go back up and down the tree, and that's a pain in the butt. We want to do it as simple as possible. You could do that, but it's not fun, right? I want a better algorithm. Like you could rearrange the whole tree, but that's not what we're trying to do. Okay, figure it out. You're getting there. Figure it out. Talk to Steve about it. See if it works out. Don't look at the tree. Try it and see if it works out. Okay. How are you guys doing?
I don't know how to remove from the middle.
Don't know how to remove which?
From the middle.
Yeah, it's tough. That's tricky. Think about that one. How about you guys? For which ones?
So we divided up into, you're either removing the root, something in the middle, or the leaf.
Okay, the root, I'm not sure the root is necessarily a special case. I like the leaf, because the leaf has how many children? None, right? What other possibilities? So you've got no children. What other possibilities do you have? One child, and then 2 those are the 3 cases. So in this case, so could you, it's pretty easy to remove 1 child, right? Like if it's a 1 child, or sorry, it's pretty easy to remove a no child. If you have no children, you just remove it. You put the parent to null and you remove it. But if it's a 1 child, how would you do it? Okay, so it's like what? It's like what have we already studied that's similar? Linked list, okay. How about the 2 children? Okay, let's see it. Let's say we're removing 2. So you're saying replace 2 with what? Replace 2 with 1. Okay. That actually works, but what if, okay, in that case, but what if 1 had a right child?
We said then you add whatever's on the right of 2 goes on like the rightmost
Ooh.
part.
So you got to traverse all the way down to the rightmost part of 1. Okay, that would probably work. Not necessarily what I would consider the best solution, but that would probably work. Yeah, good. Good thinking. How about you? No idea? Keep thinking, you'll get it. It is hard, isn't it? Yeah, it's tricky. There are lots of different cases. Lots of different cases. Yeah, good. How are you guys doing?
Good.
What's the, what do you think? What are all of our cases? You know what, everybody says that. I don't think the root is a special case here.
Yeah.
That sounds good. 0, 1, or 2 children. Okay. Okay, so what if it's 0 children?
Just take it out.
Just remove it. What if it's 1 child?
Take it.
What's that? Let's say we're removing 4. Yeah, you put the right of 2 to 3, you jump it over, right? How about 2 children? That's the tricky one. Yeah. Oh yeah? Let me see. What do you guys think?
Okay, so if you delete the whatever node you want.
Let's say we're deleting 2.
Okay, and then you go right, and then you set 2's left child to, and then you push, okay. You start at 2.
Yeah.
You delete it.
Yeah.
And then you move 1 right, and then you go all the way left.
Move 1. Oh, so you.
Go to the right child.
Okay, and then.
And then you go all the way left until you can't go left anymore.
Okay.
And then that's where you put 2's left child.
Actually, you put 2's left. So you put 1 all the way down there.
Yeah.
So the idea is that, like, if you want to get rid of 2, you put 3
Okay.
in its place.
Okay, I see. So so you put 3 in. Okay, and then what do you do with? What do you do with?
Oh, and then 4 becomes 6's left.
What if we were removing 4?
Okay.
Okay, no, sorry. What if we're removing 2? Go back again. If we're removing 2, walk me through what happens again.
Okay, so 2 disappears, it gets deleted.
Okay.
And then 1 becomes 3's child, left child.
Okay.
And 4 becomes 6's left child.
6 is left child? I'm not sure that actually. What do you think? Yeah, yeah.
Start at 2, you find 2, you use the helper function that will go 1 right,
Okay.
and then all the way left.
Okay, okay.
So now we have the next largest value
Yeah.
compared to 2.
Then, right, because it's the next large. Yeah, it's okay.
Right.
Good.
You're going to take that value and delete the node down there, that place.
Okay. Is that going to be easy? What if 3 had a right child?
It does, yeah, and then you'd have to call.
Well, believe it or not, well, you would, but is it hard to do? What's special about that 3? I like, well, in this case there's no children, but in order for the 3 to be the least child, it has to have no what? Left nodes. So it's only got at most 1 child. Is that an easy case to delete a 1 child? Let's say you're deleting 4. How easy is it to delete 4? Well, you just move 2's right to 3. Yeah. So I think you're absolutely right on this one. I think you got the right idea. We'll clarify that. Yeah. Moses, how you doing?
I was listening in on that, but yeah.
Same idea?
Yeah.
Okay. Okay, good. Great. Okay. All right, I love all the discussions. I think a bunch of you guys figured it out. At least you figured the slightly easier cases out, certainly, right? What are my 3 cases here? There are 3, and a lot of people are saying the root is a case. I don't believe that's a special case in this situation. But what are the 3 cases we have? Max.
One of them is a leaf.
If it's a leaf, which means it has how many children? 0 children.
It has 2 children.
If it has 2 children, okay, or 1 child. I might have said that in a slightly different order, but yes. Either it has 0 children, 1 children, or 2 children. Okay, those are our 3 cases. All right. So let's say we're deleting 3 is an easy one that has no children. It's a leaf. We find it. We do the little like search for it. We find it. How easy? And let's say we're at 4, and basically we're saying if the one we're looking for is the one we're deleting, we're at 4. How do you delete 3?
you point 4s right to null, not just 4, because remember it's got a right and a left. Point 4s right to null, and then don't worry about the left. Sorry, I was wrong. The left. Don't worry about the left. Point 4s. Oh my gosh, I'm standing this way and doing the wrong way. Sorry. The left to null, and then what do you do with a 3? Delete, right? I mean, it's a node, so you should probably delete it so it's not hanging out in outer space. OK, so that's an easy. So if it's a no children, it's an easy case. OK, how about if it's a 1 child? How about 4? How do we delete 4? Also pretty. Go ahead, Mackenzie.
Yeah, you just make 2 point to 3 and then delete.
Yeah, you make 2's right. I'll get it right this time. 2's right points to 3. So you basically jump over the 4 and then what? Delete the 4. OK, good. All right. Now, the other case is the 2 children. That gets a little bit trickier. I think that's what most people were like, oh boy. OK, I know we have a couple people who solved it. I'm going to let you give your reasoning at the end. OK, because I think you got the one that I would have chosen. Who else thinks they have a good way of doing it? OK, Mackenzie, I'll let you go right after Alice because you just answered. Go.
Oh, okay, fine. So I think what you do is you say, so if you're on the left branch,
On the
left.
left. OK, so we're going to delete 2. OK, let's delete 2.
Yeah, so then you point the 6 pointer on the left to 1.
OK, and then what?
And then, oh, sorry, no. So you point that to 4.
So OK, it's going to go to 4. OK, and then what?
Yeah.
The greater of the one you're deleting. OK, and then what?
Right. And then you take 1 and put it all the way on the left.
All the way on the left of this one? OK, I would buy that would work. I don't think it's the easiest solution. It would work. I don't think it's the easiest, but that's a very good answer. Like, that's a legitimate answer. I've heard some other not so legitimate answers, but OK. Mackenzie, what do you think? Same thing? OK, great. What do you have? Go ahead.
So what we came up with, me and Josh back there,
Uh-huh.
was that you, how do I put this? Let's say you're deleting the 2.
Let's say we're deleting the 2. OK.
You can take the subtree on the left and find the greatest value.
The greatest value, OK, which in this case is 1.
Which in this case is 1.
OK.
And you replace the 2 with that.
And then you replace the 2 with that one. OK, what is special about the 1 if it's the greatest one on the right? I mean, on the left.
Oh, did I say that? No, you find the...
I think you're absolutely right. I think you're absolutely right. But what's special about the 1? If it's on the left and the greatest one on the left, what's special about it?
It's not going to disrupt the tree because everything else is going to be less to it.
Well, OK, it's not going to disrupt the tree, but what's like? Let's be even a little more like low level in that. What's special about the greatest one in the whole tree? We already said that in order to find the greatest one, we go all the way to the right, and then what happens? That means that what? By definition, there can be no more to the right. You have found the one that's the farthest right of that subtree. OK, so yeah, so you could do that. You could say that it's the farthest right, and then replace that, and it makes it easy to replace because if it doesn't have a right, then it's only got how many children? At least, well, 0 or 1, at most 1 child, and it's easy to replace a node with 1 child. OK, I like that. That is definitely a solution. In fact, that's the converse of the solution that I would have come up with. OK, anybody else that has a different kind of generic answer? Yeah.
I actually have a question about that solution.
OK.
So say 2 pointed left to 1, 2 pointed left to 0, which pointed right to 1.
OK.
So then you found 1 with the greatest of those.
Yeah. Yep. OK. So let me just draw it up here. Let me just draw it up here. So you've got 6 and 8, and you've got 2, and you've got 4, and you've got 3. Sorry, you said now. What did you say? 2 was to 0, 0, and then 1.
Right.
OK.
So you
find the 1.
Yeah.
And then what do you do?
Then you set then you put 1 in 2's place.
OK.
That leaves the 0 hanging on the tree anymore.
Well, hold on. We have to delete this one. But how hard is it to delete this one? Boop. Done.
Oh, so you just put that value.
Right? You have to delete this one. And it may be that this one has a left, which is easy to delete because that means that 0 jumps right to it. And that's it. right? If it's got a left, this had to be, the left had to be negative, and it would work. OK, so you see how that one works?
Yeah.
OK, what was yours?
It was very similar. Just instead of finding the next largest on the left, you find the next smallest on the right.
It's exactly flipped, right? So what you're saying is, OK, we're removing 2. We find the what?
The next greatest to 2.
Well, OK, so how about this? Go right and find the smallest value. OK, this is the one I want you guys to use. OK, I love yours. It's the exact reverse. But here's the one I want. Here's the one I want you to. And when you build one of your own, use whatever you want. But this is the one that I'll show you because I mean they literally are the same. It's just just reversed. But if you're deleting one with 2 nodes, go to the right node and go all the way left. What did we say is what's special about something that's all the way on the left? It's the smallest, and how many children does it have to have? 0 or 1. It can't have 2 children, so we don't need to worry about, oh, how do we deal with the 2 children thing? It's easy to delete a node that has 1 child or 0 children. So go to the one we're deleting, go to the right, go all the way left, just find min of the one to the right, find the min, replace the 3, or the one we've removed with the 3. So now we've got 6, 3, 1, and 4. And then what are we deleting here? We're deleting 2. And then we have to delete this 3, which is easy, especially in this case because it doesn't have any children. We just delete it. If it had a child, we would have to then take the 4 and point it to the child on the left. See how that works? And by the way, this can be anything on the right here. It could be a huge other part of the tree. It doesn't actually matter. That make sense? Kind of interesting. That's so good job to everybody thinking about this. I like all the solutions. I think the hardest part is just remembering which one I'm asking you to remember. But it's not. But getting to the point where you go, OK, I see what's happening here. OK, in this case, if we wanted to remove 2, this is the one where we're going to go to the left, go to the right, go all the way left. That's 3. Move 3 to 2, and then we have to get rid of 3, but that's easy. 5's left becomes 4, and we're good to go. See how that works? Kind of cool. OK, good. All right, so that's how we do all these different functions in here. OK, pretty easy. Yes? Yes, you do have to recursively delete the 3 node, but it's easy because it has at most 1 child. Right? So yes, you do, but it's easy in that case. Okay, and that's kind of the whole point of doing it this way, is that it's easy. Okay? All right. The last thing I want to do is a couple different problems here. Okay? Given a definition of a node and a binary search tree, okay? Actually, can just be a binary tree. It doesn't really matter. Binary tree. I want to do a couple things. So let's first define what a node is so that we know what it looks like, right? We have a struct node, right? And it has a, let's call it int data. And then it has a node pointer to left. And it has a node pointer to right. Right? And that's our struct for a node. Okay, everybody with me there? All right, here's what I want you to do. I want you to write a little bit of either pseudocode or C++ code to figure out how we would count all of the nodes in the tree. You should come up with a recursive solution. If you want to do it iteratively, I'm not worried about it, but the recursive one is very beautiful. Okay? A recursive solution to find how many nodes you have. Okay? If you get done with that, I want you to try to find a similar function that finds the maximum depth. Okay, which node, or what's the maximum depth of your tree? Okay, all the way down one side or the other, or whatever the maximum depth is. If you happen to finish those, you could try the harder ones, which is, well, this isn't that hard. This is print tree, which is the in order tree. But the trickier one is this one, mirror. Mirror literally changes a tree from the left to the mirror image on the right. Okay? In other words, draw a tree and then mirror it using a recursive definition. It's actually pretty clever. Okay? Yes, question?
Are there any, or can you think of any applications for the mirror case?
You know, chemistry maybe. Maybe you have some tree that's based on like some chemical formulas and whatever, and you want to mirror it because something like that. You could probably, you know. And it's also just a good question because it's kind of fun. Okay, for now, you can work with your partner, with your neighbors, or whatever you want. Figure out the size. I will start to write some hints up on the board. In other words, I'll start to write the definition or the solution. Try to do that. Size and max depth. Okay. Yeah. Thank you. You have to return something. Yes, thank you. It is a nice solution, isn't it? What's that? You don't really need the else, you're right. Yeah. You know, it's funny, I think a compiler would just get rid of the else. I think a compiler would probably figure it out. I don't know, I think a good compiler, something that's good would probably do that. Yeah. It's the only other option, right? Say again? Oh, yeah. It's going to be. Well, I don't know. You do have to do like a jump, or you have to actually. If it's an else, you have to say, okay, well then I need to jump over this if it's not true. So you're right. It would be a jump, or some sort of branch. Yeah. I think so. I don't like it very much, but I normally say equals, but some people like gets, and I think a lot of people learned it that way. I think I've probably gotten to the point where I say that more often because I've taught it, and people tell me that, and I kind of. I think that's probably right. That's probably right. Yeah. How about the mirror one? Try it. Try writing it out. You have to do a swap in there. Think about it. Write it down. Here, copy the tree. Oh, got it. It's just the mirror image. Okay, did everybody think they figured out size? Let's see, somebody from that side of the room. What do you guys think for size? What am I going to do in the else here? Yes? Return what? Size. Size what? Size of the, I like size of node, arrow left. And then what? Plus 1. What happened to the right? You guys don't like the right. I see. That's rightist. Okay. Size, right? Node, right. And then plus 1. and then you're done. That's it. Right? Right? Pretty simple recursive program there, right? This is a great midterm question. It's too late now because I already gave it to you, but this is a great midterm question. I can still ask you. OK. Everybody get that, though? You're just basically saying, hey, give me the size of the left and the size of the right, and then add 1 to it because I'm a node, and then return. And if you walk through a tree, you'll see that works. This is the kind of recursive problem where you start to think, oh, I see how beautiful recursion is, and I see how it's an interesting solution, right? Because you're just saying, do the next step. Make the problem a little smaller. OK? All right. The other one was max depth. I'll give you a hint on this one. Max depth. Max depth. If node equals null, return 0, else. There's your hint on that one, too. I will give you another start for this one. Else int left depth equals, and then int right depth equals. Cecily?
I'm not sure it was right, but
OK, let's see what Cecily has to say.
so in left depth would be max depth of your left child.
Max depth of left. I'll just, in the interest of time, I'll just write it that way. OK.
Right depth is max depth of your right child.
OK. Good.
You would return 1 plus the greater one.
Yeah. If the I'll say it because of the time, but if the left depth is what?
5.
No, let's just say if. Compare. You just said if the max. So how are we going to find the max, right? If the left depth is greater than the right depth, return 1 plus the left depth. Else, return 1 plus the right depth. Pretty simple, huh? When it comes down to it, you're just calculating the left and the right. And this part happens by delving down into the tree. OK, and it actually works each time. So Sunny, you had a question.
Yeah, can we just say left depth gets 1 plus that and then compare it after?
Sure. You could say 1 plus that. Sure. Yeah, no worries. About the same. OK, any questions on that one? At the beginning of class on Monday, maybe we'll do the other two. OK? Question? Comment? After? OK. All right, anything else? See you guys Monday.